Okay, hello everyone. Let's go ahead and get started. My name is Irina. I'm an assistant professor at the Department of Statistics here. So just to tell you a little bit, I guess why Dr. Dabney asked me to substitute, this is me. I joined here 2 years ago, and my work, my research, primarily is in the area of high-dimensional data analysis and multivariate analysis. And so a lot of the things that you're learning in this class, I actually use in my research pretty much every day. So what we're going to talk about today is model selection in the context of linear model. And we will continue with this on Wednesday. I'm new to this technology, so I think what I'm going to try and do is to alternate between the slides and writing on the notebook and see how this goes. Are there any questions so far? Okay. So essentially the context that we're going to be looking at is the linear model. So here we have our response y. We have covariates x. And linear model is a very simple model. It's one of the first model that you learned about. And there's many different ways to extend this model. However, even the linear model has a lot of advantages to it. Oops. No, that this is sorry. Okay. So in particular, two things that are really good about the linear model is that it's interpretable, and this interpretability and simplicity often leads to good predictive performance. So just to try this out, so we have a linear model. I'm going to write it very generally like this. And good things are interpretability and predictive performance. Okay. However, often that's not sufficient to just do ordinary least squares, and we may want to consider some alternatives. And these alternatives are meant to even further improve the things we already like about the linear models. In other words, we want to improve how interpretable the linear model is. And the context for it is if your number of predictors P is very, very large, for example, hundreds or thousands, and all of these coefficients are non-zero, it's very hard to say what is really having an effect on y and how those things combine. Similarly, if you have tons of predictors over here, and you're trying to predict using all of them, then your predictive performance may suffer because not all of your predictors may actually be important for y. Okay. So in other words, when we talk about the prediction accuracy, a lot of times we want to control the variance. And when we talk about interpretability, we want to get rid of some irrelevant features. And the way we're going to do it is by setting some of the coefficients to 0. So in other words, so here we have the coefficients associated with x1, and we have a coefficient associated with xp, and we have coefficients for x2, x3, and so forth. And to help us with interpretability, we're going to set some beta I to 0. So generally speaking, when we address the problem of interpretability and predictive accuracy, there are kind of free subsets, free classes of methods that we can work with. So the first class is subset selection. And this is exactly going back to setting some of these coefficients to 0. And the idea is we're trying to identify which predictors are important. So let's say we have 10 predictors. I'm going to make a picture over here for that. I'm going to do the toy example. Suppose we have x1, x2, x3, x4, x5. I'm going to do 6 because I'm rounding out of space. And we believe that only some of them are important. So we want to try to identify maybe it's only these 3 that are really predictive for y, and the others are not. And the main difficulty here, of course, is that in advance, we don't know what is that subset. It could be 2, 3, 4. It could be 1 and 2. It could be all of them. So we try to identify what the correct subset is. The second approach that I don't think we will have time to talk about it today, and we'll probably discuss on Wednesday, is shrinkage. Here we are not completely getting rid of predictors, but rather we shrink some of the coefficients towards 0. And this shrinkage is often called regularization as well, and it essentially allows to reduce the variance. So roughly the idea is as follows. So this was a toy example for subset selection. So this is subset selection. Let me give you another toy example for the shrinkage. So you still have your x variables, as we started with. And you can think of fitting your ordinary least squares and getting the coefficients for each one of them. So one way to view the regularization of shrinkage is that instead of your original ordinary least squares coefficients, you get a different set of coefficients. That are essentially the original ones that are shrunk towards 0. You can shrink them towards something else. 0 is the most common thing. So again, the contrast here is that in the first case, you eliminate some of them completely, you find a subset, and often you repeat the least squares on that subset. In the second example, you do not eliminate them, but you replace the ordinary least squares with something else. And this something else could be viewed as shrinking your original least squares coefficients, your original numbers, towards essentially smaller numbers, smaller in the magnitude.
So not necessarily 0, but like...
Not necessarily 0, but closer to 0.
Okay.
Yeah. Very good question. Okay. And then the third one that looks very similar to the first is the general dimension reduction. And here the idea is that rather than looking at the original predictors, you're actually forming a new lower dimensional subspace using all of those predictors, and you're taking a lower dimensionality than P, and then you're using those new variables as your variables in linear regression. So again, I'm going to give you a picture illustration for what I mean by that. Again, my toy example. And this will be dimension reduction. So again, you have your original, let's say, x1, x2, x3, x4, x5, x6. And what you're doing, you're forming the new variables, oh, not the y. Y is what we predict. I'm going to call them z. And let's say I'm doing a smaller number of them. So let's say I'm only doing 4. So this corresponds to P was 6 and M was 4. Okay, 4 less than 6. And the idea is that each one of this is actually formed using all of them. So all of your x's go into Z1. All of them go into Z2. All of them go into Z4. So in other words, you take your original data x, you take linear combinations of them, which essentially means you're forming new variable z, and instead of using x in your linear regression, you're using the z's. And the idea is that, first of all, there are less z's than there are x's, so that's how you reduce the dimension. But also, your x's may be very similar to each other, or some of them may be very similar to each other and essentially capturing the same thing. The way you construct the z's is not only that there is a smaller number of them, but you can also construct them in such a way that each z has complementary information. So in other words, each z represents something different about the data. Okay. So these are three different approaches. Again, selecting the variables, shrinking the coefficients, and forming a new variables. And a lot of more sophisticated methods, they are not really just one of the three, but it could be a combination of all of them at once. What we'll start with today is talking about the subset selection methods. And the equivalent, or the gold standard here, is the so-called best subset selection. So I'm going to go through this algorithm first, and then I'm going to give you a short kind of a step guide on what it actually does. So the idea is that you start with something that has nothing in it, a null model. And it's essentially just having beta 0, the intercept, and no predictors. So let me illustrate that. So we're going to talk about best subset selection. It's one way to do first class of methods, subset selection. And you start with a null model, which is y equal your intercept plus nothing else. You don't use any of the x's that you have. Okay. Then what happens next is you start thinking of what is the possible size of the subset that you can have. The maximal subset size is p. The minimum will be nothing, which is the null model that we start with. We could have 1 out of x's in our model. We have 2, we have 3, and so forth. And that your model size is indexed by k. So what you do is for each possible model size k, you look for the best subset of that size. So in other words, you look for the exactly k predictors out of all of the predictors that you have. You fit the model with a set of those k predictors, and you look through all of the models, which there are p choose k of them. So why is that the case? Again, let's say we have p equals 6. So I have x1, x2, x3, x4, x5, and x6. And let's say my k is 2. Well, what it means that I have many possible subsets. I could fit x1, x2. I could fit x1, x3. I could fit x2, x3, and I go on. And the point is that there are p choose k or 6 choose 2 ways of forming a subset of size 2. And for each of them, so I can fit the model. I can fit the model for x1, x2. I can fit the model for x1, x3. I can fit the model for x2, x3, and so forth. So now I have p choose k sets of models of size 2. And what I do next, I pick the best among those and call it M2. So that will be the best model with 2 predictors. How do I define best? That's a very good and interesting question because it's debated. It's a little bit easier to answer if you look at the models of the same size as we're doing here. So we're fixing the K. Let's say it's 2. We'll look at all of these possible models where only 2 predictors are in the model. And those are the only models we compare. And in this case, we can look at the R-square value. All right, we can look at how much variance we can explain. Or we can look at the residual sum of squares. How much noise do we have left? And among all of these P choose K models, we're going to pick one. And we're going to call it M2. So now the idea is that essentially you have null model. You have M1, which was out of P possibilities. You have M2, which is out of P choose 2. You have M3, which is 1 out of P choose 3. Till the full model, just one model, all predictors. So essentially, when you think of the question of what's the best subset, it's actually a double question. First, you need to figure out, well, you need to figure out both the size, 1 predictor, 2 predictor, 3 predictors, P predictors. And given the size, you need to figure out what's the best model of that size. Yeah?
So what if I have a data set with like 26 predictor variables? Would I have to fit all possible combinations? Or is there a way
So that's why it's an idealistic thing that you cannot do in real life. It's a gold standard. 26 you can still do. As soon as you go to 1,000, you cannot do this. In computer language, this is an NP-hard problem. Which means there is not a polynomial time algorithm that will solve this problem. And what it means is that, as you can see, the size of the model grows linearly with P, but within each size, you have essentially an exponential growth. And so it's not possible to look over all possible subsets as long as your P is like, I think, currently, you can do it with 100 using some new algorithms, but that's kind of what we can do so far. You're absolutely right. But anyway, for a lot of smaller P's, you can do it. And we will see an example on the credit data set how you can do it in R. And then essentially, so where we were at. Okay, so we fix the size. For each size, we fit the best model. And then the last thing that's left, well, how do we go between the sizes? And going between the sizes is much harder than choosing within the size. And again, there's several different things you can do. What we'll talk about is how you can use different criterion such as cross-validation, AIC, BIC, and adjusted R-square. So here's going to be an example. I'm going to use the credit data set. I believe you could have mentioned it in class before, but I'm just going to remind you what the data set looks like. So each row is a person. They have an income value, credit limit value, credit rating, number of cards, the age, education, I believe is some numerical, probably the length of education. Gender, whether a person is a student or not, whether the person is married or not. Ethnicity. And the variable of interest here is balance. It's balance on the credit card. And the idea is that you want to try and understand, based on this data set, what is determining the balance that you have on your credit card. What are the factors that you can use to predict the balance? And it's it's important for determining the credit rating. It's also important for the banks to plan for how much money they have, who are the debtors, and so forth. And it's also interesting from the economical development perspective. What are the factors that influence how much credit people carry on their cards? So essentially what we have here is a data set with P, B, and 10. So we have balance is our Y, and we have income, limit, rating, cards, 10 variables that we can use to try and predict the balance. So maybe let me try to write it down. So example, it's credit. So our Y is balance, and our P is equal 10. And we're going to try to use best subset selection. So first of all, let me show you how you may implement some of it manually in R. And then I'm going to show you that there is a package that can do this for you. So what I'm going to do is I'm going to form a matrix. Actually, this one I don't need, so I'm just going to erase this one. I'm going to matrix P by P, where I'm going to store R² values for the models of size 2. So essentially, I'm going to go back to here. And rather than illustrating everything manually, we'll do everything using a package. I'll illustrate manually how to do the part relating to 2. So if I want to pick the best subset of size 2, how can I do this in R? So I'm going to call a matrix R², which is going to store R² values for all of this. Oh, sorry. For all of these different models. And essentially what I'm going to do then is I'm going to loop through all the variables that I have twice. So essentially for each of these P variables, I'm going to consider a pair to that variable. And I'm going to feed a model, the linear model in R, where I predict the balance using those two variables. Are there questions about this code part? And then for each one of those models, I'm going to save what is the R² for that particular model. So let me show you how this works. So it's pretty fast because I'm only looking at the size 2. So it's 10 choose 2 models. It's not a lot. And what you have here is essentially I have a 10 by 10 matrix because 1, 2 is the same as 2, 1. It's upper triangular, and I don't fit income with income twice. And what you can see is that the R² values change quite a bit. Actually, for the ease of illustration, I'm going to round it to 2 so you can see it a little bit better. So visually, you can see that, for example, student and age don't explain that much, whereas income and credit card rating explain quite a bit. And in fact, if you stare at this table long enough and just ask what is the maximum, the best model with 2 predictors is the model that has income and rating in it. So let's see. Best 2 predictor model, which we denote at M2, is income plus rating. And you can do a similar thing for 3 and 4, but you can see that it's going to get messy if you try to code it yourself. I kind of did 2 because it's less trivial than 1, but it's only 2 loops and not 3. So fortunately, there are people who wrote code to do that. In particular, there is a package Leaps, which I may need to install before I run it. So the package libs is actually described, it's used in the book Statistical Learning with Applications in R. And this is the package that I'm going to illustrate to do it. So after you use this package, the way it works is that essentially there is a function where the only thing you tell this function is what is your response, which is balance. And then you show which data you want to fit. And it goes for this whole list of models and find the best model for each number. So to illustrate, so here each row is M1, M2, M3, and so forth. And it goes up to M8, so it doesn't quite go fully. You can make it go fully if you want. If I only looked at one variable, you can see that there is an asterisk to rating, which means rating is the best predictor out of 10 if you only use one predictor. The second one is income and rating, which agrees, fortunately, with what I did before manually. So we did it correctly. And the free is income, rating, student, yes. Note, however, that when you do the best subset selection, it's not hierarchical. So for example, when we look at the best model with 4 predictors, it no longer has rating in it, while rating was in it when we had 1, 2, or 3. And that could happen. And the picture over here is actually a little bit more. What it shows you is if you want to plot not just the best model, but all possible models with 2, 3, 4, 5, 6 predictors, this is kind of the range of R-squared that you get for the model size. And then you can look across the models to see that after around 4 or 5 predictors, you don't really get any improvement in the R-squared anymore. It grows, I guess, up to 3 maybe. Similarly, if you look at the residual sum of squares instead, they decrease towards 0 and then they plateau. So after you get 3 in the model, you don't get a lot of additional information by adding more predictors in it. So this is, of course, the example for the, oh, yes. So the short answer is I don't know how to draw that graph because they haven't talked about it in the book. I know you can produce this graph yourself. I'm not sure if you can use libs package for it or if you have to do it manually. I can try to look it up. What you can do, let's see. You can do something like this. Sorry. I was here. So I get the R-squared for all the models of size 2. What I can try and do, I can do a box plot of all the ones that are non-zero. And that will at least tell me what the spread is, conditional on the model size. I could have also done it through the points. Oh, sorry. And this is actually a really good idea to do. Because sometimes you will have a set of predictors of size 2 that are very, very close. Actually, yeah, this is perfect. So what you can see is I go for 10, choose 2 models, and I plot what was the R-squared for each one of them. And I would argue that the ones that are around 0.8 are obviously better than the ones that are around 0.2. However, if you look at the top, like these two are really, really close. And ours just takes the maximum. That's what it does. But if you want to really understand what's happening here, then, or ask some more scientific questions, then you need to be careful and understand that essentially you cannot distinguish between those two. this other model could be as good as this one. And looking at that may give you some additional information. Does that sort of answer your question?
Yeah, it does. But I was wondering in the result of that leaps package, if I'm getting RSS somehow for each of the group variables.
You do get R squared. Yeah, you can do that as well. Let's see what you get actually. You get a lot of things out of this package. Yes, you do. I actually do that here. Sorry. Here's the R square. So the only thing here is that it doesn't plot. So it plots you the, it gives you the R square for the best model out of each size. So you can plot that. So you will see how with the model size, your R square kind of stops decreasing around 4. Oh, sorry, increasing. What it would not tell you is how close that call was within each size. And this is why this figure is actually pretty nice, because it gives you information about both. It's a little bit harder to see, but I think over here you can see that some of these dots, they cluster. And they cluster over here, so that's a good point. Yeah. Any other questions? So the advantage of this best subset selection is that, generally speaking, it's not restricted to just the least squares. So if you are doing a logistic regression or any other type of method, you are just using a different loss. So here we measured how good our model is by R square. But in logistic regression, we can use something like deviance or the likelihood and do the exact same approach and go through the subsets of different size and pick the model that way. Of course, as we have discussed, best subset selection has certain limitations. In particular, it cannot be applied with very large P. And the reason for that is going back to our notebook, is because how many models you have. So you have P models. Each model has P choose K. So if you think of the total number of models you have to cover, for best subset, it's essentially a sum, assuming I started with a model of size 1, and I go all the way to P of these combinatorial things. And this is essentially exponential in P. It gets huge really, really fast, and it becomes impossible to do it. So, can we do something else? Yes. And this is where the idea of stepwise selection comes in. So the step size methods, they are not going to explore the full set of models. So this is a full set of models. In other words, if we wanted to look at every single model and see what the R square is, this is how many models we need to consider. Step size methods only consider a subset of this full set of models. And how this subset is determined actually depends on which step method you use. So generally speaking, the stepwise selection methods are divided mainly into forward and backward. And sometimes you can do both forward and backward. So the idea is as follows. I'm going to give you a general picture and then talk in details more. So stepwise methods, generally speaking, are forward, which I think is more common for the reasons I will explain in a minute, and backward. And they're both considering hierarchical set of models. The difference is that with forward, you start with a null model and you progress to full model, adding one predictor at a time. And with backward, you start with full model, and you progress to null, removing one predictor at a time. So this is why I said that they're hierarchical, because you only do a change of one at a time. Your previous model differs from the current model by one. So essentially, with the forward, you add the variable that has the greatest improvement on top of what you already have. If we were to write it algorithmically, then you essentially start by augmenting whatever model you have with one additional predictor, and then you pick the best model among those. And the best, again, we can define as having the smallest R square, or the, smallest residual sum of squares, or the highest R square value. So in essence, we are going to go back to this picture where we have null model M1, M2, M3 up to MP. The difference is that each of this M1s now only consider a subset of the models of that size. So M2 is not going to go through all P choose 2. M3 is not going to go through all P choose 3. The models they go through depends for the forward based on what M1 was, and for the backward based on what M3 was. So to, again, make it a little bit more precise, so forward, you have null model, do M1, which is best predictor out of P. So far it looks the same. But when you do M2, you take M1 plus whatever best predictor is with M1. So the key difference is that you condition on M1, and you only add to that. So I'm going to go back to our credit data set and show you how this works and whether there are any changes. So the libs package, it allows you to do forward and backward selection procedure. You just need to change the default settings in the package. So by default, it does best subset, and I'm changing this to forward, so it's going to do forward selection. And if I do it this way, then again I get my asterisks. And now what I want you to pay attention is that each of these lines, again, corresponds to M1, M2, M3. M1 is a subset of M2. M2 is a subset of M3. M3 is a subset of M4, and so forth. So this sets of model is hierarchical. And does it give us a different answer than best subset selection? It does. If you recall, the rating disappeared at 4, because when we looked at the set of 4 best predictors, it turned out that rating was not among the 4 best. However, because rating was selected at 1, 2, and 3, and forward selection goes hierarchically, it was selected as the best set of 4 with forward selection. Okay. Yeah. So it's computationally advantageous. Why is that computationally advantageous? Well, again, this was what we did with the best subset. What we do with the forward, so we start with 1 to P, and at each point we fit P minus K models. So now this is much, much smaller than before. And as such, we can do it very fast, even if P is very large. Another advantage is that sometimes P is much, much larger than N. So we will overfit if we try to fit the full model. With forward selection, sorry, let me do the different color. With forward selection, you can decide on what is the upper limit you want to fit, you want to consider. Let's call it S. And only go up to that point. So essentially, you're growing the tree in a way. You're taking one model, then you do second model on top of that, then you do third model on top of that. But you don't actually have to go all the way to the full model. You can stop earlier, especially if your number of variables is much larger than your sample size. And it's very easy to do. It's not guaranteed to find the best possible model. And again, the reason for that is that there are 2 to the p models total. So this sum that I wrote down here is 2 to the p. And when we look at the smallest set, we're not including all of them. So that's why we're not guaranteed we're going to find the best model. And an example here, again, is the credit card data set, because the best model of size 4 was not the one that has rating in it. We actually know that. Yes?
So there's another difference between the subset selection and the forward selection / bracket selection, that in the subset selection, every model is independent from the past. But for example, like whatever model you select for 2 variables doesn't depend on whatever model you choose for 3 variables, whereas in forward and backward, they depend on the previous variable selected. Correct?
You can think about it this way. What I would say, they're all subset selection methods. The first one is best subset selection. So that does the search across everything and guarantees that you find the best. Whereas forward and backward, yes, they're dependent explicitly on what you selected in a previous step. But the way to think about it is that they are more restrictive. They are not searching the full space of models that you have, but they're essentially using the information from the previous search that they have already done to direct a new search. And because they're restricting the model space, that's where the computational advantages come in, but that's also where the risk comes in. Any other questions? Okay. So with a credit data example, this is what I showed you, and this is just a summary. So when we look at the models of different sizes, 1, 2, 3, and 4, and compare best subset with forward stepwise, they actually agreed on 1, 2, and 3, but they disagreed on 4 because at 4, the best subset know that the models with cards instead of rating, in addition with income, student, and limit, actually gives you the best R-square value, whereas forward stepwise was constrained at rating, income, and student, and could only add to that. It could not remove after it had added. So another way of thinking about it, if you are doing the forward stepwise and you added a predictor at some step early on, that predictor is guaranteed to appear in every model since then. Okay, after that. Okay, so backward stepwise, it's very similar to forward stepwise, and the only difference is the direction. So going back to my example, forward, you go from null to full. Backward, you start from full, and rather than adding, you're eliminating one predictor at a time. And again, if we go and compare backward and forward, actually, first, backward, I think, is used slightly less. And that's because it has to begin with the full list squares. And if your number of predictors is very large compared to the sample size, that you may not be able to fit the full list squares. So that's the limitation of backward. But otherwise, yeah, so you sort of decrease the size. So instead of going from 1 to p, you go from p to 1. You consider all the models by removing one of the predictor at a time, and you choose the best out of it. It searches through a much smaller model space like forward. It's exactly the same, almost exactly the same number of models that they consider. It does not guarantee the best model, so they're very similar, and that's again because it does the restrictive search. And then this point that I made, that if your number of samples is much smaller, you may not actually be able to use backward right away, but you will still be able to use forward. So let me just illustrate again on the credit. The package lips allows you to do backward. So you can just change the method. And the interesting thing here is if I look at the backward, note that my first 4 models do not have the rating in it. And I know that the first 3, actually, if I were to select the best predictor, rating would have been the best, not the limit. The backward, however, ended on the limit because it eliminated the rating first at some point. And after it eliminated one of the variables, there is no way for it to get back. So on this data set, choosing best subset selection versus forward versus backward are going to give you slightly different answers depending on the model size. On this data set, because it's small, I would argue you should use best subset because you can actually do it and you can actually see how it changes. Again, on many modern data sets, you wouldn't be able to do best subset, so you have to use either forward and backward, or ideally both, and compare the results that you get. So we talked about for the particular model size, so let's say 2 or 3, we can do best subset, forward, or backward, but we also need to choose the size. So in other words, when we go to our list, we have a list of models, M1, M2, M3, MP, and we kind of look like the R squared, how it changes, and that at some point it stops growing. But how do we really, is there a method to pick the correct size out of these models? And there is a problem here, because if you just look at the largest R square value, then as you add more predictors, your R square value is guaranteed to grow. Because you're fitting on the training error, you're getting a better fit, so your R square grows. So the trick here is to not pick the model based on the data that you train your model on, but pick the model based on a validation or test error. And that's because if you just look at the training error, your R square could be super high, but you're actually overfitting. So when you look within a particular model size, R square is good because you're only looking at 2 predictors at a time. When you're starting to jump between the model sizes from 2 to 3 or 2 to P, you need to be careful when you do R square because it's gonna try to sell you the larger model. And the idea is that there are 2 approaches generally that one can do to try and adjust for this overfitting. One approach is to try to actually understand what the overfitting is and do the adjustment. This is a little bit more theoretical, and I personally think that it's really hard to do in practice unless you really know what you're doing. Sort of the brute force approach, and I think the one that's considered the most standard, is to directly estimate the test error. And the idea is that you either create a separate or set aside some of your data to estimate the error, or you do cross-validation. I will illustrate how to do both of this in R. I think there are packages that can do it for you. I think it's really nice if you can do it yourself and kind of understand how it works. And I think this lecture is till 3:50, so that means we're going to talk about it on Wednesday. Thank you. It's 3:50, right? I'm correct. Okay. Dummy. they are treated as dummy.
They're like gender female was the.
Yeah,
But
so
is it a property of leaves package? Or
that's
is it
the
generally
lips.
done in
Yeah,
all the
so
LM models?
I didn't do it this way. So if you look at the lips, ethnicity is actually categorical, and it just created two dummy, and that's how I did it. But if you look at how I did it on my code, I actually treat it as one predictor.
Okay.
You can do both.
But would LM take care of it? This LM function?
Yeah, the LM automatically. So I think, let me see, the ethnicity. So the ethnicity is one of the last one.
Yeah.
So I think it's 9, 10, 11. So let me do. So when I fit this model, I believe it will fit it. Yeah, so see, technically I added only 2 predictors, but it's automatically took care of the categories. And that's why it's sometimes nice to implement things yourself. Because I think for this data set, if I were selecting the variables, I would probably either have the ethnicity altogether or not have it at all. But the lib does it differently, so it treats them as dummies. So you can have ethnicity yes, or no, it's a credit yes. You can have ethnicity Asian but not have a Caucasian.
Right.
Something like that. So you can do both.